Okay, for today's discussion, we will learn how to calculate the method moment and MLE. Okay, for the first question, we have random variable x with this property. So s equal to 1 is theta, and s equal to is 1 minus theta. And we are 3 data. We want to find the method moment, MLE, and the asymptotic values of MLE. Okay. So the question 1, the first part, we have to find the method moment. Okay. Okay. So we have to find this is equal to 1 multiplied theta and 2 multiplied 1 minus theta. And we can get is 2 minus theta. Okay. And then we use S power to estimate the first moment. So we can say S bar is equal to 2 minus secant h. Okay. This one is our method moment estimator. So now we can guess the secant h is equal to 2 minus S bar. Okay. And we have a data S1 equal to 1, S2 equal to 2, S3 equal to 2. So that means the S bar is 3 over 5. So it's 5 over 3. So is equal to 1 over 3. Okay. And for B is MLE. Okay. The first step is you want to find the maximum likelihood. You want to find the likelihood function. Okay. So what we have is the arrow of theta. This is equal to the product of the density. And here is the PF. And the PF can be written as this, the theta indicator function of SI equal to 1. And 1 minus theta indicator function SI equal to 2. Okay. So we can do some algebra. It will look like this. And summation indicator function SI equal to 2. Okay, that's great. In the second step, we have to find the log likelihood function. So which is this? Take the log theta. Summation indicator function SI equal to 1 plus some indicator function SI equal to 2 with log 1 minus theta. Okay. And the next step we have to solve. The first derivative equal to 0. So then let's become the linear. The first derivative is equal to theta. Summation indicator function is equal to 1. Si equal to 2. Okay. Equal to 2. And here is negative. So we can solve this. We can get the summation indicator function Si equal to 1 divided by theta is equal to, okay, and we multiply theta and 1 minus theta on both sides. We can cancel these two. And we do some rearrangement, we can see is equal to summation is equal to 1 multiply theta. Okay. And this term is equal to n. the sample size. Okay, so we can say the MLE estimator is equal to this. Okay, and then we plug in our data. So the sample size is 3, and we also the data is 1, 2, 2, so only 1 is equal to. Only 1 is equal to 1. We only have one sample is equal to 1, so it's 1 over 3. Okay. And the next step we have to check. This one is MLE. And the way we find this is you have to check the value. You have to check the second derivative of the logarithmic function. So it's negative. So this one is equal to theta squared negative. Okay, so we can see this is always negative. So this one is concave. That is find the solution in the last step is maximum. So in point the estimator is MLE. Okay, that's the second part. And the next part is we want to find the asymptotic values of the MLE. Now, this one can be approximated by the Quemalolo bound. Okay, and this is equal to the inverse of feature information matrix. Okay, so we have to find this first. From definition is the negative of the second derivative of the logarithmic function. So this is become. So where is okay? Here is the second derivative. Okay, so we copy this. So we find the average of this, negative average of this. Okay, we can cancel the negative part. Okay, so this is positive. And the average of the indicator function is probability. So this is become theta squared probability of x equal to 1. And we have the summation is I to n, so we have n in here. Equal to 2. Okay, this one is theta, and this one is 1 minus theta. Then we can get the theta n plus 1 minus theta n. Okay, and we do some algebra. This can become n theta 1 minus theta, 1 minus theta plus theta, and cancel these two. So we can get n divided theta, 1 minus theta. And we want to find the inverse of this one. So the okay. But here, this one is we don't know what is theta. So we plug in the estimator. What we have is MLE estimator. So we plug in theta has ML. So which is 1 over 3. So we can say the variance of this is equal to 1 over 3, 1 minus 1 over 3, divided by sample size is 3, so which is 2. Okay, this is approximate. Okay, that's all. That's a question. Okay, let's do the second question. The second question we have the S1 to Sn, Let me check. Yes. Now follow the density like this. Of x theta 2 theta 1 over 2 theta, the exponential negative absolute value of x theta. Okay. This one is the double exponential distribution. Okay. So you look at this. That means they have a property. The absolute of x is follow exponential theta. Okay. And we usually use the double exponential theta. Okay. The first one we have to find method moment. Okay. This one is a little bit tricky because you can see the first moment is equal to 0. That is because the density is symmetry to 0. So let's look at this. So any symmetry density have the first moment. The first moment of a symmetry density is 0. Okay. So now we have to use the second moment. So second moment is equal to integrate is this and exponential negative x dx. Okay. And this one is equal to, because they are symmetry. Sorry, I forgot a square here. Because they are symmetry, so equal to this negative x theta. So this is because density and x squared are symmetry to 0. Okay. Okay, then you can see here is the density of the exponential distribution of theta. So that means this is equal to sigma squared, because this is the second moment of the exponential distribution. So this part is the second moment of okay. And now we use this to approximate the second moment. So we can get this is equal to 2 sigma h method moment with power 2. Okay. Then we can have we do some algebra. This is the summation si squared to take the square root. Okay. So this is the estimator for the method moment. Okay. Let's do B. The B is MLE. Okay. MLE. So now we have to find what is the MLE, what is the negative function. This is a product of the density. So you will look at this exponential of the SI absolute value negative sigma. Okay. Then we find the log negative function, which is like this: log sigma negative n negative summation of si divided by n divided by sigma, and they have some constant. The constant is not important here because when we do the derivative, we can cancel the constant. So here we only care about the things with the theta, with the sigma. The first derivative of this, you can do this and positive. In the second moment, the sigma with power 2. Okay, it's needle. Okay, so then we have to solve. Go to needle. Okay, so we may have the summation of the absolute value of Si equal to n over sigma. Then we do some rearrangement, we can get the sigma hat is the average of the absolute value of xi. Okay. Then we have to check sigma hat is MLE. Okay, so we have a solution, but we don't know whether this one is a maxima point, or we have to say it's a local maxima point. Okay. So for this, we only have the only way we can do is find the second derivative. So this is equal to sigma square plus 2, no, negative 2 sigma with power 3 summation of Si. Now we can see this one is not always negative. But what we have to check is we have to check when we plug in the estimator, the solution is negative. Then that's enough to say sigma hat is MLE. So now we plug in sigma hat. So this one is equal to n squared summation of this power 2 minus 2 and with power 3 power 3. Okay, so here and here is cancel, get 2 in here. So okay, see this is negative summation of Si absolutely value with power 2, and here's n with power 2. Okay, this was negative. Okay, so we can say this is MLE. So we can write this is equal to the average of absolutely of Si. Okay, nice. So next one is find asymptotic value of the asymptotic values of MLE. So we always have to do this. The values of this can approximate by the feature information. With 1 over feature information. Okay. The I of theta is one derivation is negative power of the second derivative of the logarithmic function. So we can use this. Okay. Okay. So it become negative n over sigma square plus 2 average of the SI. Oh, sorry, average of summation of SI absolute value divided by the sigma with power 3. Okay, now we have to use the property. This one is approximated by exponential sigma. So this can be equal to the average of the absolute is equal to sigma. So now this term is equal to n sigma. So now we can get equal to n. Okay. Oh, sorry. Here's sigma. Okay. Then we have to plug in the MLE estimator. So plug in. Then we can get the values of sigma ML can be approximated by n sigma h ML with power 2. Okay, that's all.